If your job requires you to connectorize cables, then you are probably required to TDR those cables as well. This video covers how to perform the function of a TDR with a pulse generator and an oscilloscope. Understanding the material in this video will help you to understand the theory of how an actual TDR works. Let's say we have a signal generator at one end of a cable and the other end is left open. At time 0, we send the incident pulse. The pulse travels down the line and gets reflected back at time 10 nanoseconds. If the time it takes the signal to travel to the end of the line and back is larger than the pulse width that was sent, you will be able to see two distinct pulses at your measurement point. In reality, the pulse width will be larger than the time it takes the signal to travel to the end of the line and back. So there will be some overlap of the incident and reflected pulse. With that said, watch what happens as I increase the pulse width. At a pulse width of 10 nanoseconds or greater, the incident and reflected pulses are summed together. This is because the reflected pulse of an open transmission line is in phase with the incident pulse. As the pulse width is increased, there is more overlap. This is the width of the incident pulse, and this is the width of the reflected pulse, and this is where the incident and reflected pulses add together. Now, let's take a look at using a scope as a TDR in order to help get a better understanding of TDR theory. First of all, I got a pulse generator and I set the frequency to 100 kilohertz. I set the pulse width to 500 nanoseconds and the amplitude to 1 volt. I want only a positive going pulse, so I set an offset of 500 millivolts. And if we look at the scope, we can see that if I show the ground reference, we can see that I do have a positive going pulse. And notice that the pulse takes up 2 vertical divisions, and my volts per division is 1 volt. So that means we have an amplitude of 2 volts. But how can that be if I set the amplitude to 1 volt? Well, what's happening is that we have a pulse that is traveling from the pulse generator. It comes up, it sees this open circuit, and the reflection returns at approximately the same time the incident pulse was sent. So we are essentially looking at both the reflected and incident pulses directly on top of each other, adding to 2 volts. When I connect the second cable onto the T connector, we now see a more complicated pulse. Now this cable is quite a long cable. In fact, it is about 16.5 feet. So to understand why we see this pulse, we have to think in terms of what the scope sees over time. At time t1, the scope sees the rising edge of the incident pulse. At time t2, the pulse has already traveled to the end of the cable, but the scope still only sees the incident pulse. At time t3, the reflection that resulted from the open cable has traveled back down the line, and the scope now sees the incident and reflected pulses adding together. Time t4 is the time of the trailing edge of the incident pulse. We still see the reflection because it has not finished returning from the end of the cable. Time t5 is the time where the trailing edge of the reflection occurs. Now we can actually determine the length of the cable by using a calculation, and in the calculation we need to know the time from the rising edge of the incident pulse to the time that we see the reflection. So to do this, I can use the times 10 function on the oscilloscope to get a better look at that that part of the waveform. And just to get a little bit more accuracy, I can turn my volts per division to 0.5 volts, and basically I like to measure, I find I get the most accuracy by measuring at the 50% portions of the rise times. So basically I'll just move these so it's easy to read, and what we have here is 1, 2, 3, 4, 5, and we have about 0.2, so we have about 52 nanoseconds. So the speed of light in free space is approximately 11.8 inches per nanosecond. The manufacturer's datasheet indicates that the velocity factor of my RG223 cable is 0.66. To calculate the speed of the pulse in the coax cable, you multiply the velocity factor with the speed of light. The result is 7.79 inches per nanosecond. And here's the formula to calculate the length of the cable. This is to put our answer in feet. This is to take into account the return trip of the reflected pulse. We now need to enter our measured delay of 52 nanoseconds, and we get an answer of 16.88 feet. Now, with a calculation of 16.88 feet and a physical, I guess a rough physical measurement of 16.5 feet, we're only a couple inches off, so our calculation is pretty accurate. But let's see what a TDR tells us the length of the cable is. So basically I got a TDR here, and I can set up my cursors. So basically my first cursor is basically at the 0 point, because I'm seeing I got almost at 0 there. And if I go to the second cursor and I move that to approximately right here, basically you could see my ohms cursor is saying about 52 ohms, if I increase it, I'm starting to increase. I'm starting to get the 58 ohms, so that's a little too high. So at about 52, 51 ohms there, I'm actually measuring 16.5 feet. Don't know if you can see that with the camera, but it is 16.5 feet. So that is the physical measurement. So the TDR is definitely more accurate than the scope, but the calculation is pretty accurate, you know, within a few inches. You probably don't want to do use a scope as a TDR for extremely large runs, as your error will increase. You can also determine the impedance of a cable by connecting a potentiometer to the end of the cable. So basically I have this potentiometer here. I soldered it to a BNC connector, and I'll just place it on to this cable. Now this potentiometer is a 10 kilo ohm potentiometer, and it's turned all the way to one end, which is 10 kilo ohms right now. And because the 10 kilo ohms is so much more larger than the 50 ohms of the cable, the pulse looks the same as it did before when we had an open circuit. So as I adjust this pulse to, or as I adjust the potentiometer to closer to 50 ohms, we're going to see the reflection start to disappear because more of the pulse is being dissipated into the potentiometer. And right now I'm just going to set my volts per division to half a volt, and I'm going to try and match this to a perfect square wave. And at this point the potentiometer should be at about 50 ohms, and this is how you can tell what the impedance is of the scope or of the cable. You can basically take this potentiometer off and measure it on a multimeter. So basically I have this potentiometer on the multimeter, and I'm reading about 56 ohms, and that's pretty darn accurate. You know, that gives you a good idea of the impedance of the cable. So let's see now what happens when you adjust the potentiometer to lower than 50 ohms. That's higher, and we're going lower, and basically what we see here is this is a portion of your incident pulse, because in a short your reflection returns as 180 degrees out of phase with the incident pulse. So all this area right here, the incident and reflected pulse, are canceling each other out. This is where the scope sees the rising edge of the incident pulse. This is where the trailing edge of the incident pulse occurs. This is where the scope first sees the reflection, and this is the trailing edge of the reflection.